Oh, also, after today, when we talk about this mean value theorem, which we're going to get to after this, you will be able to go back and do that number 11 in the multiple choice, right? Number 11 in that packet we skipped because it was the mean, it was about the mean value. So we'll be talking about that here. All right, so here's the problem. Now, this always kind of causes us some grief whenever, over the years, it has especially caused us grief whenever we get one of these functions where you could do this. Now, I don't know how many of you did get your calculators out for this one. For part A, I think you definitely would. This one says a calculator may be used, but for parts B, C, and D, I'm convinced that nowadays this would be in the no calculator section, except for part A. The rest of this would be in a no calculator type of situation, all right? It's one of the reasons, because the CAS calculators can do this, the others would not be able to handle the B like that. So I think what they do is they don't want some people with one calculator to have an advantage over some others, and so they would move this to the no calculator. I think a problem like this is why they went from 3 and 3 to 4 and 2, as far as which ones you can use calculator. So here we go. So the first thing, you would definitely use a calculator. You would just plug a 1 in for B, a 2 in for B, a 3 in for B. And you would go ahead and you would graph them. And they came out to look like there was, one of them looked like this, and then the next one kind of came up and then came down and did this, and then the next one went up higher and then came down, right? I mean, it was something like that when you graph those various things. So now you would need to graph them and make them look kind of nice and do that. Well, we're not going to go over that part. I think everybody should be able to set a window, draw a graph, and that kind of thing. So I'm not really concerned about that part. But it's parts B and C that I want to talk about. Find the x and y coordinates of the relative, and relative means what? Relative max means local max, right? And relative min means local min. And then we'll get to part D in a minute. Now B and C, it's the same work for each part, so you only have to do it once. This was the AP test. You could say in part C, you could say refer to my work in part B, and then give your rationale for local min. Okay, so let's go to that, and let's do this. So we have this function. F of x was the cubic x cubed minus 3bx, and they told us that b has to be positive, right? All right, so we want to find a local max, and then down here local min. So what do? What do you need? You need a derivative. And set it equal to 0, which finds your stationary points. And a local max will be where that changes from positive, negative to a number line, right? Solve it for x. All right, so you do your derivative and you get what? No. Since b is a constant, b prime would just be 0. Or excuse me, yeah, be 0. But you shouldn't be doing a b prime anyway. And again, this is why I want to talk about this problem, because whenever we see that K or that B or that A, it just kind of freaks us out, and we panic a little bit. Hopefully, as we go through these, that won't happen here pretty soon. You'll start getting more comfortable with these. When you see that 3bx, just remember that that's just a number. Just treat it as just like there was a 7 there or something. And just do the same things you would do, okay? Now, yeah, it gets a little trickier. Now, they said in terms of B. Find the x and y coordinates in terms of B. What's that mean? No. It doesn't mean set B equal to.
Solve for B.
It doesn't mean solve for B. It doesn't mean respect to B either.
Leave B in there.
The answers will have B's in it. That's what it means. Find the x and y coordinates of the max and min in terms of B. Means that the answer will have B's in it. That's what that means. Okay? So that should make you feel more comfortable about it when you read that, is that what am I doing with this B? You don't have to do anything with the B. It's just going to be in there. Okay? That's what you'll be taking. All right, so we do our derivative, and we said we set it equal to 0, and then we do what? Solve for x, which means get the x by itself. So do all the normal stuff you would normally do, which would be add 3b over to the other side. Divide by 3. Do the square root, and don't forget what? Plus or minus. And what did we just find? The stationary points. And what we just found are the things we put on the number line. Right? Pretend that was plus or minus 7. With plus or minus 7, you put a negative 7 and a positive 7 on a number line. What we're going to do instead, and it's an F prime number line, that's where you plug it into. So we're going to have a negative square root of b, and we're going to have a positive square root of b on a number line. Okay? Now we need to pick things that are in between there to plug back into F prime, because we're looking to see when F prime is positive or negative. Now remember, we know b is positive, right? We want to know when this F prime is positive or negative in between there. Well, the easy one is what's in between here? 0. So that'll be easy. Let's go over here to the right. What's something that's bigger than square root of b? Okay, I heard a couple things. I heard square root of b plus 1. Now that's interesting. Square root of b plus 1. Here's why I would avoid square root of b plus 1. Because whatever I write right here, because that's true. B is positive, right? So square root of b plus 1. If you add 1 to a positive, it's going to make it bigger. But what are you going to do with that thing? What are we doing with these things we're putting here?
Plugging them back into the equation.
Plugging them back into what equation? F prime, and plugging them in for x. So then I'm going to have, so right there, I'm going to have to take square root of b plus 1 and square it, which is going to take a whole FOIL thing, right? Which is going to get kind of ugly, right? Okay, so what's another thing that's bigger than square root of b? B. Now, what did you say? Okay, let's deal with the one I heard first where they said b. B is bigger than square root of b. That is not true. That's the one everybody always says. Okay? As a matter of fact, I'm surprised more people didn't say it, because usually everybody says that. Here, when is that not true? When is b not bigger than square root of b? Or then they're equal. When it's less, but it's between 0 and 1. When it's between 0 and 1, because think about this. If b is 1/4, right? If b is 1/4, then what's square root of b? 1/2. Which of those is bigger? What's bigger? 1/2 is bigger. Square root of b is bigger than b, right? So b is not necessarily bigger than square root of b. Same thing with b squared. Some people sometimes will have to do problems where I have a number line, well, b on the number line, and somebody says, what's bigger than b? B squared. B squared might not be bigger than b, right? If b is 1/4, b squared is 1/16. B squared is actually smaller, okay? So when it's between 0 and 1, so you got to be careful with that squaring and square rooting thing. So I like, Steve, what you said. I think that would be true. You said square root of 2b. Now think about that. If b is, if you have the square root of b, if you double what's inside there and then do the square root, shouldn't that be bigger? Okay? Now, I'll be honest. Here's what I had in mind. I was thinking this. It's just as easy to square as this. Actually, it might even be a little easier. But wouldn't 2 square root of b always be bigger than square root of b? As long as you know b is positive, it would still be bigger. Because now this is 2 compared to 1. Right? So, okay, but the lesson from this is this. If you've got a letter like a B or a K or something like that, multiplying it by 2 or 3 or something like that will make it bigger automatically, even if it's less than 1 or whatever. And it's also easier to take the square or something than it is if you have a plus 1. So usually we stay away from the plus 1. And then what would be smaller over here? Negative 2 square root of b, right? And that would be, so if you had negative 3, you double it, that's negative 6, that goes farther left. All right, this is going to happen. This is not the only time you're going to see this. Almost every set of free response questions, it seems like, every test, every year, has one of the problems on it where you have some unknown constant in the function that you have to deal with. So this is not an unusual situation, just we haven't run into it that often. Okay, but we're going to start seeing it more and more. All right, so here are the things in the blue we're going to plug in. We said we're going to plug them in right here, right, for x. So let's do 0. That's easy. So you plug 0 in, what do we get? 0 times 3 is 0 minus 3b.
So it's
No, it's negative 3b. But what do we know about b?
It's positive.
B's B is positive, so -3 times a positive is negative. So we know that's going to be negative. See, without knowing what B is, we know that'll be negative. Okay, let's do the one on the right here. Let's do 2 square root of B. What do you get when you square that? Now, when you square this, 4B. You square both of them. So you get 4B times 3, 12B, minus 3B is 9B. Positive, because B is positive. So again, without even knowing what B is, we know that's positive. And then what happens over here? Well, you're going to take this and square it. Well, it's the same thing we had over here. When you square it, it'll turn positive again, right? So when you take this and square it, you'll still get 12B minus 3B. You'll still get 9B. So it's still going to be, so this will be positive as well. So, because when you plug that in for x, you're squaring. So it doesn't matter if it's negative or positive. So there we go. So what were we looking for? Local max. Where's our local max? That's the local max. This one, that's the local min. So that's going to go down in our answer in part C. You don't need to redo that work. But look what it says here. Find the x and the y coordinate. Find the x and the y coordinate. Okay? All we have is the x coordinate. So let's just do our local max one first. So let's do negative square root of b. So that's the x coordinate. How are we going to get the y coordinate? We go back into this original right here. So we're going to take negative square root of b, cube it, minus 3b times negative square root of b. Right? So I'm taking this negative square root of b, and I'm plugging it back into the original, because I need both the x and the y coordinates. So to get the y coordinates, got to go back into the original. Now, here's where your calculator, since they will do the cast stuff, see, you could have solved this on your calculator. But again, I wouldn't even bother doing it, because rarely is that going to happen. Problems like this are going to be in the no calculator. As a matter of fact, that's why they wrote them this way, with the b in there, to force you with the old style calculators, because the old style calculators couldn't handle the b. So that forced you to do it without a calculator, even though it was on the calculator part. Well, now with these cast ones, the people who had the cast calculators would have an advantage, because they could plug these in and get it to simplify a little easier. That's why I think they now put these in the no calculator, so everybody's on the same foot. Okay, so what do we got? So what do you get when you cube this? Now, I'm not saying you have to simplify this, but I think you should, because it's going to make part D a lot easier. You would still get a lot of points. If you got everywhere down to here and you didn't simplify this, you'd probably get all the points and maybe lose only one. But, you know, let's do it. So what is this when you cube it?
Negative b to the 3 halves.
To the 3 halves. Because what you have is negative b to the 1 half to the third. When you have a power on a power, you multiply the power. So that'd be 3 halves. Okay, here you'd have a negative times a negative is going to be a plus. What's b to the first times b to the 1 half? What do you do there? You add the power. Right? X cubed times x squared is x to the 5th. You add the power. B to the 1 times b to the 1 half would be b to the 1 1/2, which is 3 halves. Oh, they have the same power. Can we add those together? They're like terms. 4x squared plus 2x squared is 6x squared. Right? You can add the like terms together. So what we have is a negative 1b to the 3 halves plus 3b to the 3 halves. What's that? 2b to the 3 halves. So there is our answer to part B. And then you would do the same thing down here for part C for the minimum, which was root b, and I think it comes out to be negative 2b to the 3 halves. It seems kind of weird to put one of them as a root and the other one as a fractional power. It'd be fine though. You could have wrote that b to the 1 half there if you feel more comfortable with that. So here's your minimum. Now, I will say this. When we were doing the optimization problems, and I won't get real picky on the take-homes. I mean, I'm going to look for your justifications. If you're doing a global max-min, list of candidates, number line, whatever, I'm going to be looking for those max, the justifications, because we got to beat it. But But when we do local max min, we haven't done any of that since chapter 2 really. And I hope you guys remember what I told you about local max min. When you do a number line like this and talk about local max, you had to say, and see if you remember this, this is a local minimum, or excuse me, this is a local maximum because f prime changes from positive to negative, so therefore f goes from increasing to decreasing. Whenever you've got a local max min or an inflection point argument from a number line, you have to write that out on a free response question. Now in this packet, if this happens to be one that I grade, because I'm going to pick a couple out in each packet to grade more carefully, if this happens to be one that I pick out to grade more carefully, I'll be looking for that. It will need to say here that this is a local max because f prime goes from positive to negative, so therefore f goes from increasing to decreasing. On the test, the midterm next week, that will have to be there. On part C, you don't need to redo all this work here, but you will need that justification. You can say, hey, up in part B is my number line. This is a local minimum because f prime changes from negative to positive, so therefore f changes from decreasing to increasing.
Yeah, my question is on that. So
Yeah.
you just write the justification on the C part.
Yeah, so you'd really just need that answer in that. It's kind of a strange one to have two different parts. One's local max, one's local min. Usually those are the same part.
So should you write the number line back on C?
Yeah, I mean, it wouldn't hurt,
Okay.
but you don't have to redo all that work. But yeah, it wouldn't hurt to do that. I think on the AP test, if you refer back to an earlier part and say, something about there, but it wouldn't hurt to copy, maybe your number line or something. But I don't think you would have to. Okay? So just keep that in mind. So when you're doing these packets, the free response questions especially, if that's one that I've picked out to grade more carefully, I'll be looking for those things because those are the things I'm looking for on the midterm. You need to be in the habit of doing that so when you take the test, that you just do it. Okay? Now, if I was just grading this one as completion and going through there, I wouldn't be looking at it that carefully, and this work would probably get by. Just so you understand. All right, now let's go to part D. Now, part D, it's possible to get a lot of these points and not really understand what in the world they're talking about here. And I want to show you, because it is kind of cool, the result from part D. But it says, show that for all values b greater than 0, the local max and min points, which we just found. Okay, the local max and min points were negative root b and 2b to the 3 halves. That was one of them. And the other one was root b and negative 2b to the 3 halves. So those are the local max and min points we just found. Show that those max and min points lie on this function by finding A. So without really even understanding what in the world they're trying to get you to do, what would be your best guess at what you should do? Well, solve for A by plugging what? These points in for X and Y. Because look what it says. The max and min points that we just found lie on this function. Well, all the points on that function, that's what X and Y are. X and Y are points on the function. So let's just take this first one. Let's take this first one and let's plug it in to this function. So for Y, we'll put 2b to the 3 halves equals negative A, and then in place of X, we'll put negative root B. Right? So I'm just going to take this X and this Y and stick it into there. Now again, you might not even be able to picture what it is they're trying to get saying in this problem. But just reading that, I think about the only reasonable thing to even do is to take those points and stick them in for X and Y. I don't think there's anything else you could even think to try. So now let's work with it a little bit. So you got 2b to the 3 halves, negative A. What would this equal here when you cube that? Negative b to the 3 halves. We just got done doing that earlier, didn't we? We just did it a minute ago. This is b to the 1/2 to the 3rd. Power on a power, you multiply the powers. So half times 3 is 3 halves. So this would be negative A times negative B, and when you cube a negative, it stays negative, right? Because you got 3 negatives. So this would end up equaling just a positive A times B to the 3 halves. Over here we got 2B to the 3 halves. Now what? They wanted you to solve for A, right? They said, find the value of A. So let's multiply both sides by b to the 3 halves. We got 2b to the 3 halves over b to the 3 halves. One thing you'll notice in these free response questions, when you get into one like this, it gets kind of messy. If you just stay with it, usually some pretty nice things happen. So what do you get? You just get a equals 2. Because b to the 3 halves cancels. Oops. I'm going to put my 3 halves. B to the 3 halves cancels. Just get a equals 2. And actually, that's all you had to do. You'd be done. You'd get all the full points for going through that process. Well, no, I take it back. You have to plug this one. You have to plug this one in too. And the only thing that will happen is you'll end up with a negative on both sides, and so when you divide, the negatives will cancel. You get the same thing. You get a equals 2 again. But I think it's kind of a cool problem to see what they're saying. What they're saying is that a is 2, no matter what b is. That's the cool part of this. No matter what function you're talking about, no matter what b is, the max and min points are on this curve. Well, that's a negative cubic. A negative cubic goes down like this, right? That's a negative. This cubic right here, what this is saying is it touches all the max and mins of all those other graphs we did on the other part. So if we go back to your picture here, if you had a cubic that came up like this when b was 1, and when b was 2, you had a cubic that came up like this, and then when b was 3, you had a cubic that came up like this. Let's take a picture. But anyway, the graph, and then if you were to graph those, and you could do this on your calculator, it's kind of cool. If you were to graph negative 2x cubed, guess what it does? But it comes down like so. And it goes through all of the max and mins of all those cubics. So there'd be an infinite number of those cubics that look like x cubed minus 3bx. There'd be an infinite number of them depending on what b is. Every one of those max and mins would be on that red graph, negative 2x cubed. That's what you found in part. Okay? All right. So that's a pretty tough one, especially this first time through, not having worked with a lot of these problems where we don't know what b is or k or a or whatever, and stick those in. But it's a pretty common thing. So look for it here in the next couple of packets. I'm guessing you're going to see some more. Kind of like that Shanghai problem. It's kind of, in a sense, a little bit like that, in the sense you have those on the point. All right? Okay. So should be pretty much wrapping up sample 1 and sample 2. Some of you have come to me with just a few lingering questions, and that's fine. You continue to do that as we get closer. So let's get out your notes and open your book up, like we said there, to page 280, and let's take a look at the mean value theorem. All right, so the other day, we're going to end up with 3 theorems here, and they sound a lot alike, and their names kind of give them away. Because remember, one of the things you have to do on the quiz is you have to state those 3 theorems. Well, the first one is the extreme, and so you got to know which one's which, right? The extreme values, and we talked about extreme values, maxes and min. If f is a continuous function on the closed interval. Now, somebody asked me today if you had to write the words closed interval, if you just show a and b with the brackets, and you don't. You could just say let f be continuous on this interval AB with the brackets. That says it's a closed interval, so you don't have to write the words closed interval. if you have a continuous function on a closed interval, then f has both a max and a min value somewhere on the interval AB. Okay? Then we had this thing called the intermediate value theorem, which basically said intermediate means between. So it basically said if you have a continuous function on a closed interval, then the function's going to hit all the y values in between f of A and f of B. That was one way we said it, but the way you need to write it is more this way. Let k be any point in between f of A and f of B. Then there's going to be some point C in between there that's going to hit that point. F of C is going to equal k. All right? But k can be any point in between it, so it means basically it has to hit all the points between f of A and f of B. All right. Now, before we write the mean value theorem, I just want to jot down a couple of things, and you can put these in your notes as well if you want to. But first of all, we got to talk about this idea of a continuous function. Okay, so a continuous function is no breaks, no gaps, no holes, no jumps, things like that. This would be a continuous function, a parabola. This would be a continuous function, right? The mean graph. Both of those are continuous functions. Today we're going to be talking about the term differentiable. A differentiable function. What does differentiable mean? The derivative exists everywhere. The derivative exists everywhere. Now, another term that often goes with differentiable is smooth. Of those two graphs I have up there, which one is differentiable? The parabola is differentiable. This is not, because the derivative does not exist at that sharp point. So it's kind of the square and the rectangle. Okay? A square is also a rectangle, but a rectangle might not be a square. A differentiable function is continuous, but a continuous function might not be differentiable. Right? So the term that we often use with that is we'll say differentiability implies continuity. It means if you're often told that you have a differentiable function, if you're told you have a differentiable function, you also know it's continuous automatically. If I tell you you have a square, you also know it's a rectangle. I don't have to say it's a rectangle, you just know if it's a square, it's also a rectangle. If I tell you a function is differentiable, you also know it's continuous. There's no gaps, no holes, no. Okay, so in any of these packet problems, when it says the function is differentiable, that's a good thing. That means nothing weird's going on. Nice and smooth, no holes, no vertical asymptotes, no sharp points, none of that. Okay, kind of like when you do your list of candidates, you look to see where the derivative is undefined. Well, if a function is differentiable, there won't be any places where the derivative is undefined. Because that's what it means to be differentiable. The function is the derivative is defined everywhere. Okay. So that's differentiable and continuous. So understand those things. That could be a question on the quiz. Right? I mean, this quiz on Wednesday is about the ideas behind this chapter. The idea of continuity, what it means for a function to be continuous, what it means for a function to be differentiable. Those are things you want to know. All right. So let's go to the mean value theorem. All right. The mean value theorem. This gray thing is not level.
Oh, you're right.
No. Well, yeah, but I don't. That's true. I think that's what it is. Yes. Because it couldn't be my writing. My writing. Okay, so here we go. For the whole board, maybe. All right. So. Everything is off except for my writing, I think is what we're deciding. Okay. So the mean value theorem says, suppose f is continuous on AB. And now this is the reason somebody in the class asked this question, because I left off the word closed interval. Okay? So just writing that shows that it's a closed interval. So f is continuous on the closed interval AB, which is the same stuff we had before in our other two theorems. And differentiable on the open interval AB. Okay, now we'll talk here in a minute why we said both, because we just got in saying if it's differentiable, it's also continuous. Well, we need it to be continuous through the whole interval, including the endpoints. But it doesn't need to be differentiable on the whole interval. It only needs to be differentiable in between. The derivative has to exist in between A and B. We don't care if the derivative exists at the endpoint. So that's why we say them both. So you have to be able to say both of them. Then there exists a number C on AB. Now I could have also said between A and B. I think that's what I said on the intermediate diagram. That says the same thing. There exists a number C on the open interval AB. So it's not at the endpoints, but it's in between. And by the way, before I finish it, what do you think of when you hear the word mean value? Average. Okay, this has something to do with average. Okay? Then there exists a number C on AB for which f prime of C is equal to f of B minus f of A all over B minus A. All right. So, what's the right-hand side say? Slope between not only 2 points, what 2 points? The endpoints, right? Because A and B were defined here to be our endpoints. So the right side is a slope between the endpoints. What's the left side?
Slope, the derivative of a point.
Slope at 1 point that's in between the endpoints. So this is saying that if f is continuous on the whole interval and differentiable in between in the open interval, then there has to be some place where the slope at 1 point is equal to the slope between the endpoints. That's what it said. Now, does that make sense? It's the term, it's because remember, slope between 2 points is average rate of change, right? That's where the word average comes from. Average rate of change. And so for this to exist, we have to have points at the endpoints. We can't have open circles, right? The function has to be defined at the endpoint. So the only way we can do the slope between the endpoints is if it's continuous all the way through, including the endpoint. But it only has to be differentiable between A and B because C is between A and B. So the derivative has to exist in between A and B. So that's why we have to list both parts. Okay, so the left side is slope at 1 point. This is slope between the endpoints. Okay, those have to be, there has to be some point where the slope at 1 point is equal to the slope between the endpoints. Now the book, I've got a couple of nice pictures of this. Here is a picture that's in your book. And this helps it to be pretty clear, I think. Doesn't it make sense that if you start here and end here, and this would be the slope between them, that as you go up and down, now remember, it's got to be smooth because it's differentiable. Doesn't there have to be some place where the slope is parallel? Basically, that's what we're saying, right? The tangent line parallel to the secant line. It just kind of makes sense. It would have to be that way. Matter of fact, it probably makes more sense if you think of it this way. If I drive from here to Grand Island and average 60 miles an hour, what's the mean value difference? At some point in time, instantaneous, right? That's a derivative. You have to be going 60, right? If you average 60 miles an hour between here and Grand Island, at some point in time, you had to be going 60. That makes sense. Okay? There's a story in the book. I don't know if this is really true. I've never seen this or heard of this happening. Might be one of your homework questions or one of these items. But if you've ever been in Kansas, we always go through these when we go down the KU relays. You've been in Kansas on those toll roads where you go through the toll booth and they charge you and you pick up the ticket, you know, you get on the interstate, you pick up the ticket, and then when you get off the interstate, you go through a booth and you hand them the ticket and they charge you and they bring it up and they tell you how much it costs. So the example they talk about is if you get on the interstate, you get your ticket, it's usually stamped, you know, it's stamped where you were at when you got it and what time you were there. And then, so let's say you went 100 miles down the road and you handed them your ticket. And so the story goes, you hand them your ticket and they look at it and it's an hour later. So that means if you went 100 miles in an hour, you averaged 100 miles an hour. So as the story goes, they say, so that you had your ticket, and you pay your money, and then they hand you your change and a speeding ticket, you know. Because according to the mean value theorem, you just averaged 100 mile an hour, so they know for a fact at some point in time, you probably were going over 100, but they wouldn't give you a ticket for that, right? Because they don't know if you were going over 100, right? But they know for sure if you averaged 100, at some point in time you were going 100, so they can give you a ticket for 100 mile an hour. Now, like I said, I don't know that really happens. I've never heard of it happening. I don't know if they can even legally. I don't know that those workers that are probably getting minimum wage sitting in the toll booth are allowed to hand you a speeding ticket. So I'm not sure that actually is happening.
Mr. Clark, if that would have happened, you probably would have gotten one speeding to get handed to
When
the
you
bathroom.
guys went to the bathroom, that's true, because did I have to get off? Oh, no, there was no way back on, so we didn't have to go through the toll booth, did we? Yeah.
But you were
So I was
speeding.
definitely speeding, but then we were stopped at the bathroom, so that probably offset. Those would have offset. So, but that's, I mean, so it is kind of common sense, okay? It is kind of common sense, and then I've even, so we can see it in motion, but this is kind of the same thing. And so here's the slope between the endpoints, and so at some point, and in this case there's a couple of places, but again, only if it's smooth. I mean, you can see there's gonna be another place coming up here where it happens. There's one, but there would be some others, but only if the curve is smooth. Well, why is that? Because technically it's because the derivative is continuous. In other words, that tangent line has to pass through all those various slopes, right? It's kind of like the intermediate value theorem in a way, right? It's got to pass through all those different slopes, and at some point it's going to equal that slope. But now, what if it's not differentiable? See, and then this is the thing. So let's go back to this picture here. What if this was your A and your B? Right here and here. Is there any point in between there that has that blue slope? There isn't one. But that doesn't violate the mean value theorem, right? Because of what? This function's not differentiable. This function does not go through all those different slopes because it's got that sharp point. I mean, that's what a sharp point does, is cause it to drastically, instantly change slope instead of being smooth and go through all the different possible slopes. And that's what's going on. Okay. So what would a potential problem look like? Might look something like this. It might say, show, I mean, this could be on Wednesday's quiz, a simple calculation, but show why the mean value theorem, why does the mean value theorem say that for this function on the interval 3 to 5, why does the mean value theorem say there has to be some point C where the derivative equals 8? Why does there have to be some point C in between 3 and 5 where that has to equal 8? And if it is, then where is that point? So what would you have to do to answer that question? You would have to find f of 5. See, now somebody in the other class said just do the derivative, which is 2x, set it equal 8, which is 4. Well, that'd be part of the solution, but that's not the whole solution, because the problem said show why the mean value theorem says that somewhere the derivative has to equal 8. So what would you do? You'd have to do f of 5 minus f of 3 over 5 minus 3. F of 5 is 25. F of 3 is 9. Which would equal 16 over 2, which would equal 8. In other words, what you just showed there is that the slope between the 3 and 5 is 8. So according to the mean value theorem, somewhere in there, the slope has to be 8. And then if they said find that place, then you would do your derivative and set it equal to 8 and find it. And sure enough, 4, which is in between there, the slope does equal 8. But I would want to see this work on your paper right here. Okay? I want to see that setup. So if there's a problem with the mean value theorem where you have to show according to the mean value theorem that something's happening, well, basically what the mean value theorem says is this right here. So this little formula better be in there. Okay? So it has to do with the slope between the endpoints being equal to the derivative at some point. All right, the real value of the mean value theorem is the theory, though. The theory that we don't get into very much in calculus. But I want to do one short, little, simple mathematical proof for you to show where this can be used. And it has to do with the chart. All the stuff in the chart is stuff that I told you, we put it in the chart, it all makes sense to us, but we never prove it. And mathematical stuff like this, at some point in time, is proven to be part of the mathematical system. Well, the mean value theorem can prove almost everything that's in the chart. Let's do one of them here together real quick. You would not have to do this on the test, okay? But one of the things that's in the chart is this. If f prime is greater than 0, on some interval, all the way through any interval you want, a, b. So if the derivative is greater than 0 all the time on this interval a, b, then what do we know is true? According to the chart. F is increasing on that whole interval. Right? And that's one thing in the chart. If f prime is positive, then f is increasing. That makes sense. F prime is a slope, so it's positive. The slope is positive, means it's going up. Okay, it makes sense. But how do we really prove it mathematically? Well, we use the mean value theorem. Here's what we do. So according to the mean value theorem, now we're going to assume this is a differentiable function, right? This is a differentiable function now. So if it's a differentiable function, we know, according to the mean value theorem, we know this to be a true statement, right? Right? We know this is a true statement because the mean value theorem says we didn't prove the mean value theorem. That would be more complicated, right? But it is true. Okay, so the mean value theorem has been proved, and so it is true. Okay, so here's what I'm going to do. I'm going to multiply b minus a over this side. Okay, we know this is a true. Oops. We know this is a true statement, so I'm going to multiply b minus a over this side. So I would have this. Now, in this problem, tell me what I know about f prime of c. F prime of c has to be positive because we just got it saying that f prime is positive in that whole interval a, b. C is somewhere in between a and b. Okay? So c is someplace in between. Okay, so we know that's positive. What about b minus a? Why? Well, wait a minute.
It's because it's increasing, so B will be bigger than past.
Yeah, the interval goes from A to B, right? And when we write an interval, A is to the left of B. So that means B's got to be bigger than A, right? So B's got to be bigger than A, so B minus A's got to be positive, right? So what that just told us is that this side right here, f of B minus f of A, has got to be what? Positive, right? It's got to be greater than 0. So this side's got to be positive. Well, for that to be positive, I'll just add f of A over to the other side. F of B's got to be greater than f of A. Well, now that's y values, right? So for any interval a, b that I pick in here, this is telling me that f of b, the y value to the right, has to be bigger than the y value on the left. What's that mean? No, well, I already know this was positive. It means f is increasing. That's the definition of increasing. Is if a function is increasing if the y values on the right are always bigger than the ones to their left, right? So this right here says f is increasing. So we started with the mean value theorem, which we know to be true, multiplied that over. We were given that f prime was always positive, right? If f prime is positive. So we knew f prime is always positive. We know this has to always be positive because b is bigger than a. So that tells us this has to be positive, which tells us f of b has to be greater than f of a, which says f is increasing. So we just proved that right there, that little simple thing just proved that if f prime is positive, then f has to be increasing. So what's so important about the mean value theorem? It's this. Think about what the chart was. The whole point of the chart was to find the connections between f and f prime. That's why the mean value theorem is important, because it's an equation that connects f and f prime. So anything we want to prove that connects f and f prime can be proven using the mean value theorem. Okay? You're not going to have to go through and do those things. Okay? You have to state the mean value theorem, have to be able to answer a question about the mean value theorem, kind of like the one we just did here a minute ago. Like here, you have to use it, that kind of thing. You don't have to do a proof, like what we just did. All right, so in a minute, we're gonna do the homework on the mean value theorem. Turn to page 288 real quick. Oh, while you're doing that, there's one other thing I need to show you. So turn to page 288. And while you're doing that, I want to show you something called Rolle's theorem. Rolle's theorem is just a offshoot of the mean value theorem. Matter of fact, a lot of times it's called Rolle's corollary. A corollary is like a minor theorem that follows directly from another theorem. What Rolle's theorem says is that if you have a differentiable function, okay, continuous on the closed interval, differentiable on the open interval, and if f of a and f of b are the same, what's that tell you? Think of the mean value theorem. What's the mean value theorem say?
Flat spot.
Yeah, the slope between the endpoints. Well, what's the slope between the endpoints if f of a and f of b are equal?
0.
0. The mean value theorem says there has to be some place where the slope is that. Slope is 0. In other words, there has to be a stationary point, right? That's what Rolle's theorem says. If you have a continuous function on a closed interval, differentiable on an open interval, and f of a is equal to f of b, that basically tells you the slope is 0. Then somewhere in there has to be a stationary point, which makes sense. If you start here and come back to there, at some point you had to turn around, the slope had to be 0. Okay? So you won't have to have that. I won't ask about that on the quiz Wednesday. But it's just an offshoot, which could be important because we are always interested in where the derivative is 0. All right. If you look at page 288, there's a nice kind of summary of the stuff in chapter 4. So somebody in their class was asking about the quiz, what are some of the things? We'll talk a little more about this tomorrow, or give you a chance to ask questions. But here's kind of what I'm thinking for this quiz. It's no calculators, less short answer, true, false, that kind of stuff. So maybe some definitions. There are a lot of bold-faced terms here in chapter 4, so maybe kind of some definitions. You can do those as true, falses, or you write out the definition. Again, it wouldn't have to be a word for word kind of thing, but say what something is. It'd be kind of a short answer kind of thing. So, bottom page 288 talks about slope fields. So you're not going to have to draw a slope field. You're not going to have to calculate a difference equation or anything like that. But might ask you what a slope field is. Slope field is a graphical solution to a differential equation. Okay, which it talks about again. The solution is the original function, right? So the slope field is a graphical solution to a differential equation. Okay. So you might be asked something about slope fields. What are they? That kind of thing. Next paragraph there's about limits. Probably not going to be anything about limits. Okay, because that's pretty much working them out, that kind of stuff. We already did a quiz on that, so you won't have that. Optimization. Not going to be any story problems that you have to work out optimization. We did our take home, we did our other quiz. Okay, that's over. But I might ask you about the process of optimization, right? We've talked about this. What are the three things, where are the three places you look for global max and min? Derivative 0, derivative undefined, endpoints, right? Okay. What's a stationary point? Where slope derivative is 0. What's a critical point? Derivative is 0 or undefined, right? Those are critical points. I mean, so those kind of terms. I might ask about those kind of terms, critical point, stationary point, or how we look for, where we look for maxes and mins, that kind of thing. Parametrics won't be anything on parametrics. Related rates won't be anything on related rates, because it's just working out the story problems. The next paragraph, we didn't do that section, linear approximation, we didn't do that. Newton's method, you won't have to work out a Newton's method, but you have to understand the process. You might have to describe Newton's method somehow or whatever. So you need to know that Newton's method is to help find roots of an equation. And it's to, we make a guess, we do the tangent line, we ride the tangent line to the x-axis, solve that equation, then that's our next guess. And then it's a repetitive process that we do over and over until we approximate that solution.
So is there any actual math on this?
Well, I mean, I showed you that one where you had to do like the average rate of change kind of thing. Yeah, is there any calculations? No, that's what it said. That's what I just said. Kind of no calculator. Yeah. Yeah, it's not. I mean, this would be one of those. This could be a note card one, right? You make those note cards and study up. But yeah, this is more short answer and just answering questions about that. So that was Newton's method. And then the last thing is continuity and differentiability. So what's it mean to be a continuous function? What's it mean to be a differentiable function? And then state these three theorems. I mean, the last two sections, the theorems, that's a big part of the quiz. Then these other things will be mixed in there as well. But the homework we have in section 4.8, you know, right, if you were 37 miles from home and then 6 hours later you're 12 miles per hour from home, what's that say? You know, and so you kind of went through that, well, you had to be all those different distances in between there at some point in time or whatever. You know, those kinds of questions could be some that could be on there. And then today's homework on the mean value theorem, those kind of things could be on there as well. And you'll know as you go through and see those. Okay? So, I'm going to let you go ahead and get to work. The last homework assignment on the sheet there, the 4.9, is your homework for tomorrow. I don't think it takes a real long time. It all has to do with the mean value theorem. And then I would suggest also, because we have 2 packets to get done this week, or before Monday. Now actually these last 2 packets won't be handed in until Tuesday. First 2 will be handed in on Monday before the first midterm. And then the last 2 will be handed in the next day on Tuesday. Now my suggestion is you'd pretty much be done with the packets, I would hope, you know, by Monday, you know, because that's the first midterm, so you'd want to have it done probably. But, and you should have an opportunity. But, so this pack gets started on this next pack. I don't have a really cutoff of how many you should do, but you should be getting started. Tomorrow we'll have a fair amount of work time in here probably. Okay? And this is packet 3, it says exam 2. Okay, so that's, 4.9 homework and then get started in this third packet. All right, rest of the time is yours to work.
So sample 1